Hello, my name is Ken Nakagaki. I'm a fifth-year PhD student at the MIT Media Lab Tangible Media Group. So this place is my home lab, and in this video I'm very excited to share my latest research paper named HERMITS, which was explored and developed in my home lab during the lockdown 2020. In this paper we present an idea to enrich the interactivity of self-propelled robotic tangible user interfaces using mechanical shell add-ons, which are basically external passive attachments to the robotic tangible user interfaces. So in the field of HCI, research in actuated and shape-changing tangible user interfaces have been widely explored to embody dynamic digital information through physical shapes. Researchers have been investigating to develop a generalizable configuration of actuated TUI hardware that can provide a variety of functionality and usability with a single hardware. On the other hand, power of motion and actuation in kinetic art or mechanical automata has been a great inspiration for us. When you look into these works, each specific art pieces or sculpture can only create very specific motions, but each of them can provide a very rich expressiveness in their motions. So having these as a background, we have this research question of how we can empower the actuated TUIs in terms of one, richness of display, animation, and expression capability as you've seen in the mechanical automata, and second, adding the reconfigurability for a versatile tangible interactions so it can adapt to a variety of applications. So to move step forwards, we have got the inspiration from biology, hermit crabs. Hermit crabs, as you know, shelters themselves into empty seashell and interchange the shell according to their body sizes as they grow. So in our paper, HERMITS, named after hermit crabs, intends to contribute to this effort by introducing an addition of passive mechanical attachments, which we define as mechanical shells. While the self-propelled TUIs have limited interactivity, the passive attachments greatly extend the capability of the core hardware. So in the past, researchers have developed different types of tabletop actuated tangible user interfaces where the tangible objects can move around on top of the desktop surface to embody digital informations. Recently, there are lots of research in approach to embed the locomotion capability of actuated wheels in tangible objects, including swarm user interfaces. We define these approach as self-propelled TUIs in our paper and seek for a way to extend the interactivity with passive material modules. So extending the interaction of generic interactive devices using passive objects has been explored in HCI to extend the interactivity of smartphones, displays, or even 3D printers. In the context of actuated TUIs, activating passive material have been widely explored using shape displays as well as self-propelled TUIs. For example, researchers have explored ways to simply handle solid objects, moving them around. There are investigations in assembling blocks into different shapes. And animated craft is another one to create playful storytelling applications. In our work, we focus on extending the motion-based interaction with passive module embedded with mechanisms that has been explored partially using shape displays. We think there is an open research space to explore this idea with the self-propelled TUIs. So as a quick summary of the contribution of HERMITS, we introduce a general methodology to enrich the interactivity of self-propelled TUI with mechanical shell add-ons. We introduce the definition and design space of the mechanical shells, and we talk about the implementation of our proof-of-concept prototype. We present 3 application spaces to motivate the concept, and lastly, we show an open research space to motivate the general approach for the future research. So mechanical shell is a term we define in our paper as external passive attachments to self-propelled TUIs that can be automatically attached or detached. So as you can see, mechanical shell can have a variety of form factor or interactivity in the self-propelled TUIs dynamically or selectively attach and detach to the other. So while each mechanical shell can provide a very specific interactivity and functionality, as a whole, the system architecture can provide a very versatile, adaptive, and reconfigurable interactivity to the users by interchanging the mechanical shells. The overall design of HERMITS would look like this. The system includes the self-propelled TUIs controlled by the computer, and these robots can be actuated to dock to the mechanical shells to create the reconfigurable interactivity to the users. To explore a variety of mechanical shell design, we have defined a primitive design space which became the basic vocabulary for design of the mechanical shells. For example, shape is the simplest property to be converted by interchanging the mechanical shells. They can also extend light output by using optical fibers to extend the indicator LED of the hardware. Extension of the motion is the key property in the design space. For example, the rotation of the robotic hardware can convert to vertical linear motion. Also, the speed and torque of rotation can be converted to achieve specific tasks such as generating wind or walking over uneven surfaces. Mechanical shells can extend the sensing capability of the robots for detecting reconfigurable tangible input, which can be utilized for dynamic physical affordances. In this case, we are showing knob and slider example. One of the very unique features of HERMITS is that multiple modules of self-propelled devices can cooperate together to activate single mechanical shell. With this capability, for example, the robotic devices can achieve rather complex interactivity or motion with much degree of freedom for robotic application or I/O devices. Additionally, the multiple robots can work together to assemble together or to generate the greater speed or force either by stacking to each other and rotate or pushing single mechanical shell in parallel together. So this design space became the basis for a variety of mechanical shell examples we created and demonstrated in our paper. So as for implementation of the system, we employed and modified an off-the-shelf two-wheeled robotic toy named Toio to prototype the concept of HERMITS. One of the primary modifications we made is the addition of vertically moving pin for docking. So when they ride into mechanical shells, they can have a robust connection to the mechanical shell embedded with the female docking slots. With this, even when the user picks up the device, the robotic device won't fall off from the mechanical shells. Using Toio API, we have developed the control architecture. Single Raspberry Pi can control up to 5 Toio via Bluetooth, but we can use multiple Raspberry Pi to be controlled by a single computer to handle the input and output. So it's basically a scalable system that allows us to create a very large-scale interactive setup to explore a variety of interactivity. Also, one of the uniqueness of this Toio setup is that they can detect the absolute position on the special mat by the camera embedded into the Toio. On the other hand, we also developed peripheral functionalities. For example, the system can track the position of the mechanical shells using a camera and markers. We have also employed joysticks to manually control Toyo robots for prototyping different interactivity, which we used when exploring the applications. So we have also defined 4 primitive designs of mechanical shell, which became the basis for our prototype to convert motions in different ways. Each of the 4 designs provide the different characteristics to convert the interactivity or motion of the robotic TUIs, and details are summarized in our paper, but these became the basis for us to develop a variety of mechanical shell examples. So in terms of applications, we have developed 3 different application or use cases in HERMITS. Firstly, HERMITS can be used for physical space reconfiguration, for example, for adaptive and assistive desktop. We believe this is very promising direction to be deployed beyond the desktop or other physical space in our everyday life, because people are already having these robotic vacuum cleaner, for example, that are moving around in our physical space. It's really exciting to imagine how we can fully expand the capability and functionality of these robotic systems in our physical environment by adding passive mechanical shell attachments. It can also be used for interaction with digital data. In our paper, we discussed the use for tangible mobility simulation, where mechanical shells can be interchanged to represent different vehicles or agents in simulated urban model, but in dynamic tangible form. Usually, these simulations are shown or interacted only in the screen, and we are very excited to think of how this can be physically, dynamically embodied with the HERMITS. Animated storytelling demonstrates to convey story by interchanging the mechanical shells, where each robotic module acts as an actor on the stage. They can switch the mechanical shells just like changing costumes in the backstage in the theater and appear on the front stage for interactivity. As for conclusion in our paper, we propose the HERMITS and define the concept of mechanical shells. With this concept, we have developed both the overall system design as well as the design space of the mechanical shell. Based on this design space, we have demonstrated a variety of mechanical shell examples. We prototype and introduce the implementation of our proof-of-concept prototype, and we describe application space to motivate this new concept. So with this, we are very excited that this idea is the first step towards a very bigger open research space. For example, the future research space could include updating the self-propelled devices to other hardware such as drones, which can freely move around in the 3D space to dock to mechanical shell. What if the mechanical shell can be fabricated on demand instead of only having prefabricated or assembled mechanical shells? We also need advanced control algorithms to orchestrate the swarm behavior to be able to dock and undock in an architecture. We are very curious to look into doing user study and explore the higher level interactivity with this new hardware configuration. Lastly, the research has been explored under the vision of radical atoms, which envision the future of physical material that is coupled with dynamic digital information. We believe the idea of HERMITS is proposing a very interesting perspective or paradigm in the radical atoms research. In the past, there have been investigation in 2 primary approaches to develop this idea of digitally empowered dynamic physical materials. One is self-activated machines embedded with motor power and computation, and another is passively activated machines that is activated in response to external stimuli, but with no embedded motor computation. I believe our paper HERMITS in high-level context brings a new perspective in novel hybrid architecture, basically coupling these 2 approaches to be reconfigurable for adaptive tangible interaction, and we believe there's a lot of research space to be explored along this generic approach. With that, I would like to thank my co-authors, including Joanne Leong, Jordan Tappa, Joao Wilbert, and Professor Hiroshi Ishii. And if you have any comments or questions, please feel free to reach out to me. Thank you very much.